Okay. Um, First, some logistics stuff. It says in the syllabus that next week is the first lab exam, but we've only had one lab. So we're going to push that out a little bit. I'll put this in the D2L announcements. But lab exam 1 is going to have to be pushed back 2 weeks because we were going to have lab exam 1 and then the regular exam 1. So let's do lab exam 1 the next week after the regular one, you know. So lab exam 1 is going to be pushed back 2 weeks. Just so we can cover a little more material first. And then exam 1 isn't next week, but it's the next one after that. So the regular exam is going to be like the syllabus says, you know. But we're going to push back the lab test. And then I just posted the first weekly assignment. So you have like a week to work on that. Let's see. So if you go here, you can see that it's due, you have 9 days to work on that. And it's not a terribly time consuming thing. So, but that just gives you a lot of flexibility to fit it into your schedule. And remember those weekly assignments, you know, I don't grade the daily assignments. You have the solutions for those, but these weekly assignments, I do grade carefully, sort of the way I grade exams. So, and they're worth more points too. So you want to make sure that you take that one seriously. It also will give you sort of a clue on how I'm planning to grade the exams and what kind of things you'll see on the exams, okay? So think of it kind of like as a run through of what the exam is going to be similar to, you know? Anybody have any questions about any of that? Okay. The next thing that we're going to talk about is, we've been doing the constant acceleration equations. And you can use these anytime the acceleration stays the same over the full motion. But now we're going to talk specifically about the one most important application of constant acceleration. So the most important application of constant acceleration is free fall and projectile motion. I'm going to use these words sort of interchangeably. But what these mean is the only significant force on the object is gravity. So when can you treat something like it's in free fall or projectile motion? You can think of there as being two requirements. The first one is that the object isn't touching anything. And the second one is that the effect of air resistance is negligible, it's small. So the effect of air resistance is negligible. And we'll get in today, we'll get a little bit into when you can expect air resistance to have a big effect and when you would expect it to have a small effect. So free fall and the acceleration that gravity applies to things is one of, I mentioned when I think the first day of this class that there are a few cases where you have sort of strong intuition built up about how things work, and that intuition for most people is wrong. And in those cases, you have to go back and be very sort of explicit to yourself about like, okay, I need to recalibrate the way I think about this stuff happening, okay? Free fall is one of those times. So I'm going to call this common misconception number 1, okay? This is the first big misconception that we're seeing in this class that a lot of people have. So common misconception number 1. And this isn't a reflection on you. This is something that the smartest scientists in the world until the 1700s, 1600s at least, had this same view, but it's not right, okay? So it's often believed that when a light object and a heavy object fall, gravity makes the heavier object fall faster. So gravity makes the heavy object fall faster. And it's not hard to think of examples that make you believe this could be true. Think of going to the top of a building and dropping a balloon at the same time as you drop a big rock. The rock is definitely going to hit the ground faster. There's no question about that. Okay, but the truth is it's not gravity that does this. And if there was no air resistance, the balloon and the rock would fall exactly the same way. And that's hard to kind of believe until you see it, but I'm about to show you a video where they remove the air from a room and you can actually watch things fall at the same time. So the truth is gravity makes all objects fall with the same acceleration the thing that makes objects fall differently is just air resistance. How air resistance reacts, affects different objects differently. So the differences in how objects fall is just due to air resistance. On Earth, if you don't get too far away from the surface of the Earth, so even if you're in an airplane or whatever, that's still, think of that as the surface of the Earth. You're still pretty close to the surface of the Earth by astronomical measurements. All objects that are not significantly affected by air resistance accelerate down at 9.81 meters per second squared. Okay. Anybody have any questions about this, what I'm saying? So this is something you're going to need to knock around in your head a little bit, probably, to undo the way you picture things that turns out not to be right, So I'm going to show a video now from YouTube. Okay. And hopefully the sound's going to work here. So
this is NASA's space.
Okay. So anyways, to set this up, this is a well-known physicist, Brian Cox, and he's in this place that's designed for testing aerospace equipment. And they have powerful pumps in this that can suck almost every single molecule of air out of this room. And when you remove air from a room, you remove the air resistance. And so they're going to first take these things, a feather and a bowling ball. They're going to drop them. The bowling ball is going to smash into the ground. The feather is going to flutter down. And then they're going to go through this, I'm sure, very expensive process of sucking all the air out of this room. And they're going to drop them again. And what I said is that these two things, once the air is removed, are going to fall exactly the same. The feather is going to fall exactly the same way the bowling ball does. Okay. And you're not going to see any ripples in the feather or anything like that. It's pretty weird to see, but that's what's going to happen. Is there air in this room right now or not? How can you tell?
He's alive.
He's alive, exactly. That's how you know there's air in there. Also, if he was in there, besides just that you need to breathe air, if he was in here wearing like a scuba tank or something, and they sucked all the air out, the pressure around him would go to zero. The pressure inside his body is still atmospheric pressure, and he would explode. That would be really gross. So he's not going to be in there when they suck the air out.
Power facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Okay, so first of all, you're not crazy. That's what happens. Like, you haven't been like imagining what happens when you drop a feather. A feather flutters down to the ground. Okay.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
That's slow motion. I wish they just showed it full speed. All they show is slow motion.
Look at that.
They came down exactly the same. Wow.
Exactly.
You're back on the side.
So, I mean, that's pretty amazing though, right? I mean, that sort of goes against the way you tend to think about things happening. But the only thing that's keeping feathers in a bowling ball from falling exactly the same is that air resistance has a bigger effect on feathers than it does on a bowling ball. Okay. Well, someone mentioned a balloon earlier. What would happen if you dropped a balloon in this? So what if you dropped the balloon with the air in the room and then you pumped all the air out and then dropped the balloon again or whatever? What would happen? There's weird stuff that happens with pressure. Yeah.
I was going to say, like, wouldn't the air of the balloon cause it to pop?
Exactly. That's exactly right. Because a balloon right now, when you pump it up at atmospheric pressure, it's fighting against, it has a pressure on the inside that's fighting against the atmospheric pressure. And that's what's making it this big. So if you get rid of all the pressure on the outside, it would blow up. Then pressure is an odd thing. Okay. So the next question is, how do you know? So when we do calculations involving free fall and projectile motion in this class, we're always going to assume that we can ignore the effects of air resistance. Okay, we're going to assume like everything is happening inside that vacuum chamber. And for some objects, that's a really good assumption. And for some motions, and for other objects like feathers that you drop, it's a terrible assumption, and you'd get results that don't match what happens unless you're in a vacuum chamber. So how do you know how much air resistance is going to affect the motion of objects? So let's go through a list of the things that, like how air resistance affects things. Okay, so these are the things that determine the effect of air resistance on an object's motion. The first one is the mass of the object. If two objects are identical except for their mass, like think of a pinball and a ping pong ball or something, you know, they're the same size and shape, but their masses are very different. So if two objects are identical, except for their mass, the object with the larger mass will be less affected by air resistance. So if you dropped a ping pong ball and a pinball, and forget about the fact that the ping pong ball would explode with no air around it, say that this ping pong ball was manufactured where there was no pressure, so it doesn't have any pressure on the inside either. If you drop these two things with no air resistance, they'd fall identically, just like in that video. But in regular air, if you drop a pinball and a ping pong ball at the same time, the air resistance is going to slow down the ping pong ball, and the pinball is going to accelerate pretty close to 9.81 meters per second squared. It has more mass, so its motion is affected less. The ping pong ball has less mass, so its motion is affected more. Anybody have any questions about that? Okay, so mass is the first thing. More things that have more mass are going to move closer to the way they do in a vacuum chamber. Okay, things that have less mass are going to be more, their motion is more different than a vacuum chamber. Okay. The second thing is surface area. So things that have a bigger surface area are going to be more affected by air resistance. So a bigger surface area means an object is more affected by air resistance. And that's really one of the, probably the biggest thing that the feathers have that makes air resistance affect their motion a lot, is they have a huge surface area. They're also light, but if you dropped, say, a marble and a feather, they might have about the same mass, you know, but if you dropped a marble and a feather at the same time, the marble would fall much more as if there was no air resistance than the feather would. The feather would flutter. Think about, you know, a person jumping compared to a person jumping out of an airplane with a parachute on. The masses are similar, you know, but the parachute is designed with all this surface area to make air resistance affect the motion as much as possible to slow you down. Yep.
In a vacuum, would a parachute not work?
It would not work. You would just fall straight down. Yep. Same with a helicopter. Don't ever try to fly a And actually, helicopter, you know, there are always, like every year, mountain climbers in the Himalayas, you know, die, bad storms come and whatever. And I think a lot of people's first reaction is like, why so stingy? Go get them in a helicopter, you know, they're just sitting out there. And the thing is, as you get to higher altitudes, the density of the air gets lower and lower to the point that helicopters just can't fly up in the highest mountains, you know. Even getting to the base camp of Mount Everest is a tough job for a helicopter that would be very dangerous to do in even mildly bad weather, you know. And higher than that, they just can't go. And it's the same thing, like helicopters, you don't really think of it as air resistance that the rotors encourage, but those rotors are creating air effects, and that's what lifts the thing. And if there's no air, they're no different than a bowling ball or a marble or whatever, you know. And then the third thing, and the most important thing actually, is speed. Faster objects are more affected by air resistance. And the reason this is the most important of the three is that in the equations that determine the effect of air resistance, speed is the only one that's squared. So as the speed increases, the effect of air resistance goes up much faster than that. And this explains why in races of objects that aren't going very fast, aerodynamics isn't a major concern. Like if you watch distance runners in the Olympics or World Championships or something, they're just wearing regular shorts and whatever. That, like, they're obviously not too concerned about air resistance. But if you're talking about a car trying to break the land speed record, everything is air resistance. It's almost the only consideration. You know what I mean? So it's because as speed goes up, air resistance goes up as it's square. It goes up much faster than that. Okay, any questions about those three things? Mass, surface area, and speed. Yes?
So they are in order of importance?
Really, the first two, it's hard to say one's more important than the other one. It's only the third one that appears differently in the math.
Okay, so let's say an object like had the first two and it's favored to fall faster, but then the third, like then the second object had like speed on its side, which one would fall faster?
It's hard to say without knowing specifically. But one thing that this thing about speed says that it's not just the object that matters, you know? It's also what's happening to that object. Like, for example, how much does air resistance affect the motion of a baseball, you know? Well, if I drop a baseball from here to the table, it doesn't affect it at all. Like, you could assume no air resistance and get perfect results almost, you know? But if you're talking about a ball that's been hit in a, you know, by a professional hitter, it's gone 450 feet or whatever, it's been going really, really fast, and air resistance affects its motion then a lot, you know? So it's not just the object, it's also what's happening. Any other questions? Okay. So all that stuff is kind of just background for your own information or whatever. If you can ignore air resistance and, you know, air resistance isn't having a big effect on the object, then you can assume that objects have a downward acceleration at 9.81 meters per second squared. And so in free fall and projectile motion problems, you always know what the acceleration is. Okay. So let's start doing some problems. I'm going to use the same approach for constant acceleration that I used in objects rolling on ramps and things like that. But now we're also going to know what the acceleration is. Okay, so first, let's say that you're on a bridge. Let's say there's no boats going under it. Don't do this if there's boats going under it. And you want to know how high this bridge is, okay? You don't have a tape measure long enough, but let's say there's a rock on the bridge, you know, and you have a stopwatch, okay? So you can drop this rock off the bridge into the water and time how long it takes to hit the water and use that to figure out the height, okay? And we're going to use the constant acceleration equations to do that. So, so let's say that's the bridge. There's the water. I don't know why I drew it like this before, but I'm going to keep doing it because it's funny. Okay, so there's the guy. I don't know. This is you on the bridge. I don't know why. Drawing faces is hard. Okay, so let's say it takes 1.2 seconds for the rock to hit the water. How high is the bridge? We're going to go through the exact same steps that we have in other constant acceleration problems. So what's the first step in a problem like this?
Choose your.
Exactly. So we're going to choose our positive direction, our zero position, and our time equals 0 and our time final. I'll choose the 0 position to be the level of the water and the positive direction to be up. In free fall problems, you're going to notice I just always choose my 0 to be sort of the lowest point in the problem, and I always choose my positive direction to be up. Not because that's a better way to do it, but really just because it helps to always do it the same way. You make fewer mistakes. So that's what I'm going to do. And then we have to choose our instant when we turn on the stopwatch and our instant when we click the stopwatch off. So what's the instant we're going to turn the stopwatch on? Yep. So the instant that you drop it. And when are we going to turn it off? Yep, the instant it hits the water. And one thing, I'm going to bring this up a few times, but this is the first time we've seen it. In order to do these calculations, the acceleration has to be the same through the whole motion, okay? Which means we can't assume that anything is going to change when the rock hits the water. So really what we're doing is a calculation where we're clicking the stopwatch off when the rock reaches the level of the water, but nothing changes when it reaches that level. The velocity isn't affected by the water or anything like that. Do you understand what I mean? If we did say something changed when it hit the water, say we assumed that the speed went to 0, that would mean that the acceleration wasn't constant and our answers would be wrong. Okay, so really time final is when it reaches the level of the water, but it doesn't actually touch it. Or you can think of it as the instant right before it touches the water. Okay, we've got these. So now the second step is we have to figure out what variables we know and what variable we're trying to find. So I'm going to list out all the variables. Time final, acceleration, P initial, P final, V initial, V final. Okay, time final. Do we know what the stopwatch says when we click it off? That's right, perfect. So we know that time final is 1.2 seconds. Do we know the acceleration? Yep, and you have to think about the sign. I have my positive up. Gravity accelerates things down, so it's negative. Okay, so acceleration is negative 9.81 meters per second squared. Do we know the position of the rock at time 0 when we click the stopwatch on? No, correct. Well, we don't know what that is. That's what we're trying to find. Do you see that? It's so we're trying to figure out how high the rock was at the instant we let go of it.
PI, right?
Yes, thank you. Do we know P final?
0.
0, perfect. So P final is where we put our 0 position, so this is 0. Do we know V initial? We do know this, and actually I meant to say this a second ago, but whenever something is dropped, at the instant it's dropped, the velocity is whatever the velocity is of what it's dropped from. So if it's dropped from a car, it starts out with the velocity of the car. If it starts in an elevator, when you let go of it, its velocity is the velocity of the elevator. If it starts from a bridge and you drop it, the velocity is 0. Okay? Unless it's a very bad bridge. You really want bridges to have 0 velocity. That's one of the main things you look for in a bridge. Okay, so this is equal to 0. Do we know final velocity? No, it's going to keep speeding up as it goes. And so we'll just leave that out of there. Okay, is there an equation that lets us solve for PI and everything else in the equation is known. The one that will work is this one. PF is equal to P sub I plus V sub I TF plus 1/2 A TF squared. And so let's check and just make sure that it works. PI is in it, so that's good. And now we'll go through everything else that's in the equation and make sure that it's known. So PF known, VI known, TF known, A known. So this one will work. So plug in all the values. 0 is equal to PI plus 0 times 1.2 plus 1/2 times negative 9.81 times 1.2 squared. So 0 is equal to PI. This one goes away because it's 0 times something. The second one comes out to be negative 7.06. So add 7.06 to both sides and you get that PI is equal to 7.06. Since we did everything in SI units, this is in meters. And so that's the answer. About 22 feet, something like that. Any questions about that?
So how would, I know like 9.81 is like constant.
Yeah.
But why was it negative?
Okay, yeah. Because gravity always accelerates things down. And I had chosen the positive direction to be up. So anything that's pointing down is negative. Okay, the next question is, maybe you have a bridge like this that you'd want to check this way, but first you want to figure out how mad someone would be if they're riding a boat underneath when you drop this rock, you know? So how fast is the rock moving when it hits the water? Okay, so first thing is, do we have to change any of our choices? You never have to change your position equals 0 or your positive direction. Those can be whatever you want. Sometimes you do have to change your time equals 0 or time final though. Is there any reason in this case to change those? No, and the reason that we know we don't have to is because we're trying to calculate something at one of the two instants we already chose. Okay, so we just know it'll work. The only reason you would ever have to change this is if it asked for something at an instant that you hadn't chosen as one of your instants. Okay? So we'll keep the same P equals 0, positive direction, time equals 0, and time final. And that means that all the stuff we knew before is the same now. So our TF is still the same. Our acceleration is still the same. Our PI, we didn't know that before, but now we do, we just calculated it. So now we can use this. PI is equal to 7.06 meters. P final is the same as it was before, 0. V initial is 0. And we're trying to calculate V final. Okay, so what equation works here? It looks like there are 2 equations you could use. This one, V final is equal to VI plus A times time final. And this one, 2A times the quantity PF minus PI is equal to VF squared minus VI squared. Well, if you have a choice, always use this one. It's just the simplest one. There's the fewest complications that can come up. So this equation says VF is equal to 0 minus 9.81 times 1.2 and so V final is equal to negative, I think that's 11.77. Actually, can someone just plug that into a calculator real quick and make,
Yes.
okay.
Negative 11.77.
Yep. Okay, so there's our answer. Does it make sense that we got a negative answer for that velocity? Yes, because our positive is up and the object is moving down. Okay, is the object speeding up or slowing down during this process? It's speeding up. Gravity is making it speed up on the way down. And that makes sense with the signs of our velocity and acceleration because they're both negative. And remember, an object that's speeding up has velocity and acceleration in the same direction. Okay? Okay, let me get this in your notes here. I should have done this before I did that example. But here are 2 facts that are going to be useful a lot of times in these free fall and projectile motion problems. I'll just call it free fall. But 2 facts that will be useful in free fall problems. The first one is the one that I just told you during that problem. When an object is dropped, at the instant of release, its velocity is the same as what it's dropped from. So when you release an object, its velocity is the velocity of the vehicle you drop it from. Okay, after that it can change, but right at that instant you let go of it. The second thing that's going to be useful is if an object is launched up, then it reaches its highest point when its velocity is 0. reaches its highest point when its velocity is 0. It sort of makes sense if you think about it this way. So you launch this thing up. The fastest it's going on its way up is when you launch it, and then it slows down, slows down, slows down with an upward velocity. And before it can go back down and start having a downward velocity, it first has to cross having 0 velocity for an instant. Okay? So it's like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then it starts going -1, -2, -3. Okay? Also, think again about the sign of the acceleration. Yeah.
So you're saying that velocity has zero, but let's say like baseball, right?
Yeah.
We're tracking horizontal velocity of the
Yes.
baseball. The batter hits it, well, it's
Yeah.
as positive. Does it cross into 0 or does it go straight to negative velocity?
Yeah. Yeah, that's a really important question. So right now we're doing 1D motion. Okay, so right now, if you're doing free fall problems in 1D, you can only deal with things that are being dropped straight down or being thrown straight up.
Okay.
So you're thinking of something that's like a baseball you hit, you know?
Well, I just
Yeah.
mean along the track that the baseball travels, it still wouldn't be.
Yeah, if it goes straight up,
Yeah.
then it gets to 0 velocity and then starts coming down. But if it's
Like somebody hits it, well, it's going up, does it still pass through the 0 velocity?
Oh, well then, so this is only true for something that has constant acceleration. So if something else applies a force to it, then it doesn't work anymore. You know what I mean? And also if this thing is traveling horizontal, we'll see this when we talk about 2D motion. Like imagine if someone hits a home run ball, you know, and you think like, oh, I'm gonna get, somehow you know someone's gonna hit this home run ball. You know where it's gonna be at the highest point. You're like, I'm gonna put a big ladder up there and put my head right where the ball is gonna be at its highest point because I know the velocity is gonna be 0. Well, it doesn't work in 2D, unfortunately. So that ball will still hurt your head very, very badly. But we'll talk about that when we get to 2D. But if this ball went just straight up, even if it went a mile in the air, you know, when it leaves the bat, it's going so fast. But you could just be standing there with your hand right at the highest point it's going to reach, and it would just gently nuzzle into your hand, and you just hang on to it or whatever. It would have 0 velocity. At the instant it hit your hand, it wouldn't be moving at all. Oh, I know what I was going to say. So let's think about the sign of the acceleration again, okay? So I said whenever something's in free fall or projectile motion, the acceleration is down at 9.81 meters per second squared. What about when an object is launched upwards? Is its acceleration up at 9.81 or what happens there? The answer is even when it's on the way up, its acceleration is down at 9.81, okay? And think again about what it means for something to be slowing down, because you know if you throw something up in the air, it slows down until it starts coming the other way, okay? Well, when it's on the way up, its velocity is up, okay? If it's slowing down, that means its acceleration has to be the opposite direction. And so even when it's on the way up, gravity is accelerating it down. Okay? Then when it reaches its highest point, it starts coming down and speeding up because then at that point, velocity and acceleration are both down. Okay? Let's do another calculation. Okay, so another example problem. So let's say a ball is thrown straight up into the air from a height of 3 meters. So first, oh, I didn't give you all the information yet. At the instant it's thrown, at the instant it's released, its speed is 10 meters per second. So first, how high is the ball at its highest point? You know, what's the highest height that it reaches? And then second, what's the velocity of the ball when it reaches the height it was thrown from? So it's going to go up, reach its highest point, come back down. Let's say the person who threw it caught it again. What's the velocity when he catches it? Okay. What's the velocity of the ball when it falls back to the height of 3 meters? Okay, so let me draw just a little diagram of what's going on. So here's where it's thrown from. It's going to go straight up. It's going to reach its highest point, and then it's going to come right back down. All this is happening just in a straight line. This height is 3 meters. Like I said before, for these kind of problems, I always choose my 0 position at the lowest point in the problem. So that's usually the ground or the water or whatever. And then I always choose my positive direction up. And you could get perfectly good answers with different choices of those, but I just always do it the same way. What do we want to choose as our time equals 0 when we turn the stopwatch on? Yep.
As soon as the ball is thrown up.
Yep. So yeah, time equals 0 is when it's the instant it's released. And then for part A, what's going to be time final?
When it reaches its highest.
Yep, that's right. So time final is going to be when it reaches its highest point. Okay, so now let's go through the variables and figure out what we know and what we're trying to find. Do we know what the stopwatch says when it reaches the highest point? Nope. We're not trying to calculate that, so I'll leave that off. Do we know the acceleration? Yep, perfect. Do we know the initial position, the position when it's thrown?
3 meters.
Yep. Positive 3 meters. Do we know the position at time final? No, and that's what we're trying to calculate. Do we know the velocity at time 0? The speed is 10, and be sure you think carefully about the sign. In this case, it is positive because it's moving in the direction I chose positive. But remember to always think about that. So V initial is positive 10 meters per second. And do we know V final? We do. And actually, anytime a problem mentions the highest point, you should be waiting to say V final. Like, this is your time to shine, you know what I mean? Anytime you're calculating something at the highest point, you know you're going to use the fact that V final is equal to 0. Okay, what equation works? This one should 2a times the quantity PF minus PI is equal to VF squared minus VI squared. So we have 2 times negative 9.81 times the quantity PF minus 3 is equal to 0 squared minus 10 squared. So this says negative 19.62 times the quantity PF minus 3 is equal to negative 100. Divide both sides by 19.62. Divide by negative 19.62. And you get PF minus 3 is equal to I think that's going to be 5.08. And then add 3 to both sides, and you get that PF is equal to 8.08 meters. So 25 feet or so. Any questions about that part? Okay, so now we're going to calculate how fast the ball is moving. What's the velocity of the ball when it reaches the thrower? Okay, it reaches the height that it started at. Anybody have any guesses or educated guesses or uneducated guesses about what that velocity is going to be?
Negative 10.
1,000. Yeah, it's going to be negative 10. And that's not just because of the numbers I chose. The fact is, if there's no air resistance, any object in projectile motion or free fall has the same velocity on its way up at a given height as it does on its way down at a given height. Okay? Which is why mayors are always telling you not to shoot guns into the air for 4th of July or whatever, you know. I mean, there's a lot of air resistance on a bullet because it's going really, really, really fast. But if there were no air resistance, it would come down at exactly the same speed as it goes up. And that's really bad for you if it hits you, you know. And even with air resistance, it's going really, really fast. Okay, so let's calculate this and see how it works. Is there any reason to choose a different time equals 0 or time final? This is the first one we've seen where you can't use the same time equals 0 and time final because we're trying to calculate something at an instant that isn't one of these two. Okay? So you can keep the same time equals 0. You can keep that the instant that it's launched or thrown or whatever. But the time final now has to be when it returns to that height. Okay? So our time equals 0. That can be the same as it was. But our time final has to be when it passes 3 meters height on the way down. Okay, so for variables, we still don't know time final, so why am I writing it there? Acceleration is still negative 9.81. Initial position is still 3 meters. Now we know position final too is also 3 meters because that's what we're asking about. Our initial velocity is positive 10 meters per second, and we're trying to calculate VF. We're going to use the same equation we did in part A. So I'm just writing this here for if you're looking at it later, hopefully it'll help make things clear. That's the equation we're using. So we have 2 times negative 9.81 times the quantity 3 minus 3. You see that? Because PF and PI are both 3. And this is equal to VF squared minus 10 squared. Well, 3 minus 3 is 0, and 0 times anything is 0. So all of the stuff on this side goes away. And so what we get is 0 is equal to VF squared minus 100. And so VF squared is equal to 100. And now this is the last important thing about this example problem that you have to notice. When you take the square root of a variable, the answer can be plus or minus, right? So if I take the square root of both sides now, we get that VF is equal to plus or minus 10 meters per second. Well, when this thing's on its way down, is the velocity positive or negative? Negative, because my positive I chose up. So the answer for the velocity is negative 10 meters per second. But the speed is exactly the same as it was on the way up, just the opposite direction. Any questions about that? Okay, well, I'll give you a couple problems to do that are like that. Remember to look on D2L for the weekly assignment. Get started on that when you get a chance. And I'll give an official update on D2L about when the lab test is and stuff like that. All right, see you later.